Let us now do an example problem from the quadrilateral chapter. This problem is considered to have a medium level of difficulty, but we will break it down into simpler steps so that it becomes much clearer to understand. Okay, so let us first understand what the problem is and what we are supposed to prove, and then we will approach the problem by breaking it down into simpler steps, which will make the process much clearer. Okay, so we are given two parallel lines termed as L and M. So that's a parallel line L and a parallel line M intersected by a transversal P. So that's the transversal P intersecting the two parallel lines L and M. It is required for us to show that the quadrilateral formed by the bisectors of the interior angles is a rectangle. Okay, so first of all we have to understand what do we mean by the bisectors of the interior angles. So the diagram for this question is given in this figure here. So let us first understand what are the interior angles for these parallel lines intersected by the transversal. Okay, so when we have these parallel lines L and M intersected by the transversal P, or the line AC, that is. So the four interior angles for this configuration are the angles PAC, which is this angle PAC. So that's one interior angle. Let me mark that. PAC is one interior angle. And then we have the angle SAC, which is this interior angle, SAC over here, this angle. So let me mark that as well. So the next interior angle is SAC. And ACQ is the third interior angle, which is ACQ. So the interior angle is this one, ACQ. And the fourth interior angle is ACR, which is ACR, which would be this angle over here. So we have these four interior angles. And it is said that there are four bisectors of these interior angles. So we have this line AB bisecting the interior angle PAC. So PAC is bisected by the line AB. Similarly, angle SAC is bisected by the line AD. So this line AD is bisecting the interior angle SAC. The interior angle ACQ is bisected by the line BC. So this line over here is bisecting the interior angle ACQ. And the line CD is the bisector for the interior angle ACR. So these four lines, which are the bisectors of the four interior angles for this parallel line configuration with the transversal. And we are to show that these four lines, where they meet at the B and D, the quadrilateral formed by the intersection of these four lines is a rectangle. Okay, so the requirement is, what we have to show in that problem is that the quadrilateral formed by the bisectors of the interior angles is a rectangle. So from this configuration, basically, we have to show that the quadrilateral ABCD, which is ABCD, this is a rectangle. Okay, for that, we are going to approach this problem in three steps. The first step is we need to prove that this quadrilateral is first of all a parallelogram. Once we have proven that this quadrilateral is a parallelogram, we can then prove that one of the angles for that parallelogram is 90 degrees, which will then make that parallelogram a rectangle. So to prove the quadrilateral ABCD is a parallelogram, we have to show that the pair of opposite sides are parallel. That means we have to show that AB is parallel to DC. Okay, that's the first step we will do. We will prove AB, the line AB is parallel to the line DC. Okay, in the second step, we will prove that the line BC is parallel to the line AD. So once we have proven these two steps, we would have proven that the quadrilateral ABCD is a parallelogram. Thereafter, we will prove that one of the angles of this parallelogram is 90 degrees, and we know from theorem regarding parallelograms that if one of the angles is 90 degrees, then all the other angles will also be 90 degrees, and therefore that parallelogram will become a rectangle. So let's do that in the 3 steps. The first step, as I said, will be proving that the line AB is parallel to the line DC. So this is our first step. We are going to show that the line AB and DC are parallel. So AB, let me mark that line AB with a red line here. So we are going to show that this line and the line DC are parallel. So to prove that, we are going to look at this parallel line configurations for the line L and M, and we can see that angle PAC, which is this angle over here, is equal to the angle ACR, which is ACR, which is this angle over here. So these angles are equal. Why? Because they are alternate angles for the parallel line configuration intersected by the transversal. So we are going to prove that the lines AB and DC are parallel. For that, we first have this condition that angle PAC is equal to the angle ACR, which is this angle. So why is that? Because they are alternate angles. Okay. So if these are equal, then half of the angle PAC must be equal to half of the angle ACR. So half of the angle PAC is nothing but this angle here. That's half of the angle PAC, and half of the angle ACR is this angle over here. So these are also going to be equal because we are dividing this equation by a common factor of half or multiplying by half. So half of PAC is nothing but BAC. Why? Because the line AB is bisecting the angle PAC. So therefore, half of that angle will be the angle BAC. Similarly, half of the angle ACR will be the angle ACD, which is this angle over here. So what we have now is the angle BAC is given to be equal, or is shown to be equal to the angle ACD, which is, let me use a different color for that. So here we are showing that this angle here is equal to this angle over here. So if these two angles are equal, then what we have is the line AB and the line DC is cut by this transversal AC, and the alternate angles are equal. So BAC and ACD are alternate angles for the lines AB and DC cut by the transversal AC. So when two lines intersected by a transversal have alternate angles equal, that can be true only when those two lines are parallel to each other. So since these alternate angles, which is BAC and ACD, are equal, it implies that the line AB and the line DC are parallel to each other. So we have proven the first step, that the line AB and the line DC are parallel to each other. Okay. The next step is to prove that the line AD and BC are also parallel to each other, and we will approach a procedure similar to what we have seen here, but on the other side using the other angles, and we will go on to prove that the line AD and BC are also parallel. So that would be our second step, which is to show that the line BC and AD, BC is this line and AD is this line, are parallel. So let me mark that. So BC is this line over here and AD is this line over here, and we are going to show that these two lines are parallel. Once we have shown that these two lines are also parallel, then we can show that the quadrilateral ABCD is a parallelogram. So for this again, we notice that since the lines L and M are parallel cut by the transversal P, the angle SAC is going to be equal to the angle ACQ, which is this angle over here. SAC is this angle over here, is equal to the angle ACQ, which is this angle over here. So these two angles are same. So if these two angles are same, then half of those angles must also be the same. So half of SAC must be equal to half of ACQ. but half of SAC is nothing but the angle DAC, right? So half of SAC is the angle DAC, which I will mark here. So that's half of SAC, which is the angle DAC, marked by this blue angle here. And half of the angle ACQ is the angle ACB, which we will mark here. So this angle here. Okay, so these two blue angles, if you look at it, it is as if the line segments AD and BC are cut by the transversal AC, and the angle DAC and ACB are alternate angles. So these are alternate angles which are equal for the lines AD and BC cut by the transversal AC. And if the alternate angles are equal, it means that those two lines AD and BC are parallel to each other. So we are showing here that AD and BC are parallel to each other. Okay, so we have shown that BC and AD are parallel. So that's BC parallel to AD. Make the correction here. That's AD, not AC. Okay, that's AD. Okay, so we are showing here that BC is parallel to AD because angle DAC and ACB are alternate angles for these two lines cut by the transversal AC. So BC is parallel to AD, and previously we have shown that AB is parallel to DC. So we have now in this quadrilateral a pair of opposite sides parallel to each other. So that means the quadrilateral ABCD is a parallelogram. So we have proven the first step that the quadrilateral ABCD is a parallelogram. That means it's a quadrilateral which has its opposite sides parallel to each other. The final step would be to show that one of the angles in this parallelogram is 90 degrees. So we are going to show that one of the angles is 90 degrees in the quadrilateral ABCD. To do that, we are going to again use the angle PAC and the angle SAC. And if you look at this line L on which the ray AC is standing, the angle PAC and the angle SAC form a linear pair. Okay, so PAC is this angle over here and SAC is this angle over here. So for the line L on which the ray AC is standing, these two angles form a linear pair of angles. For a linear pair of angles, if you recall from our chapter on lines and angles, the sum of the linear pair of angles is 180 degrees. So that means angle PAC plus angle SAC is 180 degrees. And if we now multiply this entire equation with 1 by 2, so we get half of angle PAC plus half of angle SAC is half of 180 degrees. That is 90 degrees. So half of PAC is nothing but the angle BAC. So half of PAC is the angle BAC, and half of the angle SAC is nothing but the angle CAD, which is this angle over here. And what this equation is telling us is that this angle BAC plus the angle CAD is 90 degrees. So if this angle is 90 degrees, that means the sides AB and the side AD are perpendicular to each other. So we have shown here that one of the angles in this parallelogram is 90 degrees. So basically we are showing that this angle here between AB and AD is 90 degrees. So if one of the angle is 90 degrees for a parallelogram, as we have seen earlier from a theorem, that the remaining three angles will also be 90 degrees. So when we have a parallelogram with all the angles equal to 90 degrees, then it becomes a rectangle. So we have shown here that the quadrilateral ABCD is a parallelogram in which one of the angles is 90 degrees, and therefore the quadrilateral ABCD is a rectangle. So we have proven here that the quadrilateral formed by the bisectors of the interior angles for these two parallel lines intersected by the transversal is indeed a rectangle. Okay, and we did this by breaking the problem into 3 steps. The first step is we proved that the line segments AB and DC are parallel to each other. In the second step, we proved that the line BC and AD are parallel to each other. And then in the third step, we have shown that one of the angles is 90 degrees. And if one of the angles in a parallelogram is 90 degrees, then that parallelogram is a rectangle. Hence, we have proved that this is the quadrilateral ABCD is indeed a rectangle.